We're gonna move then on with the next talk. Let me introduce the speaker. It's our own Júlia Borràs. She's a tenured researcher at the Spanish Scientific Research Council. She obtained a European PhD degree in 2011 at the Institute Robotica y Informática Industrial. After she worked abroad for 6 years as a postdoc, 2 years at Yale University and 4 years at KIT in Karlsruhe. In 2018, she was awarded Ramon Llewellyn Scholarship, on my pronunciation today, one of the most prestigious senior postdoctoral scholarships in Spain. Her research interests include parallel robots, whole body motion, analysis, humanoid robot locomotion, grasping, dexterous manipulation, and robotic glove manipulation. I myself was fortunate enough to have a collaboration with her 2019 and can only say positive things. So, Júlia, take it away.
Thank you for this awesome introduction. Let me put the timer so that I can control the time. So I'm going to talk about analyzing and representing. Can you hear me and see everything?
Yes, it's fine.
Okay. I'm analyzing and representing cloth manipulation tasks. So the first thing that we can realize when it comes to cloth-like objects is that when we manipulate them, the first thing we do is grasping them. All the grasps are intrinsically non-prehensile, not only because we do platform grasps as normally, but also because not all the object is grasped. So we don't put all the object inside the hand. Also, most of the tasks are bimanual, and we also have different friction requirements because a lot of times when we humans manipulate cloth, we sometimes slide over edges, for instance. So that means that sometimes we need to firmly grasp, and sometimes we need to be able to actually slide on the cloth. From a robotic point of view, that means that we need to change probably the friction of the fingertips. And of course, then the elephant in the room is like the high deformability, which implies a very high dimensional configuration space, which means that it's difficult to estimate the configuration of the cloth, but also that both the hand and the environment, they will conform shape to this object, which is very relevant in the moment of when we are manipulating it. So that the environmental constraints are essential, and we actually use it when we fold, as we see in this picture. We use the table to support our manipulation and to be able to accomplish the task. So in a manipulation task, normally there is like this different process in parallel where we have a decision-making tool that is going to decide what is the action that we execute. Then we have these planners that decide the trajectory of controllers so that we are able to execute this action. And then at some point to monitor it and to recognize where we landed, we need to identify the state so that the decision-making can keep deciding on things. This is normally the execution loop, and what we see is that with cloth manipulation, one of the main open challenging is this state recognition and how we define it, which is basically the focus of this workshop. So state of the art has focused mainly on representing and grasp cloth state. It's difficult enough, of course. So for these are, for example, 3 examples of the main different configurations, which is completely crumpled, flat on the table, or folded. So what we propose and what we are working on is adding to this state definition on information about grasping and what is the grasping state of the cloth, and also information about the environmental contact. So basically for us, this is all part of the grasping. So we are going to assume that the environment is also grasping the cloth. So that means that if we can represent a finite number of states and we arrange them as a graph, that's what we are trying to do, that we think that this can simplify both the state recognition, because we are going to simplify the number of states that we need to identify, but also it can be as itself easily interpretable as a decision-making tool. But also we can store parameters for execution. For instance, the location of the vertices or the grasping or the interesting grasping points or the edges, etc. And in addition, what we want is to be able to learn that from human demonstrations, which right now this is an open question because it's difficult to get data from real cloth manipulations in general. So in this context, our initial proposal is this novel representation of a task as a graph of transitions between a scene states. And each one of these scene states are different moments of interaction between the cloth and the grasp and the grippers. So different moments, where is it grasped the cloth? How is it grasped? And we have basically just semantic labels describing the cloth, if it's crumpled versus if it's flat or if it's folded. And then we are able actually to learn that from human demonstrations. And we have called this the cohesion graph because it gives like a coherent overall view of the task. This is an ongoing work that we are actually still developing. So if we pay closer attention to one of these stage definitions, here we see that there are 3 levels of information. The first one is on grass type, then the grass location and the cloth configuration stage, which I'm going to interlate. So the first thing that we did when we started this work is focusing on grass type, which normally nobody has really done in the past, as we will see now. And this is a work that we published in Transactions on Robotics on a grasping-centered analysis for cloth manipulation. So the first thing that we realized when we started working on cloth type for cloth is that while normally now there is all these novel soft grippers that they adapt to the shape of the object, what happened in our case is that is the cloth that is completely shapeless and adapts to the shape of the hand. So that means that we cannot really use the classic grasping type definition that mainly depends on the object shape. We don't have shape. So for cloth, we thought is that this grasp tape must depend on the shape of the hand, because this is the shape that is going to be given to the cloth. So then we look actually in the bibliography. Here we see several executions of robotics cloth manipulations, and we can quickly realize that they all use the pinch grasp, which of course things are complicated enough, and already with the pinch grasp, these are not the focuses of these works. But then if we review also the grippers that have been used to manipulate cloth, we quickly realize also that most of them, they rely on pinch grasp, at the most in pinch combinations. But we see some interesting already manipulations with grippers against surfaces, for instance, for flattening. So that's already something interesting there. And also there are very few objects where they consider other geometries of fingertips. So for instance, here we see like some linear fingertips that they conform more shape to the object. So what we proposed in this Transactions on Robotics paper is to define grass type for cloth, for textiles, using prehension geometries. That's very basic. So we focus first on points and lines and planes, which we notate that as a P, L, or pi. And also we consider this extrinsic dexterity following this in this paper from Ann Mason, where we consider that external contacts are also grasping elements. That means that this point, line, and plane can also be geometries from the environment. Then we put this subtitle, the E, which means the extrinsic, and then we just combine geometry. What did I do now? Oh, okay. We just combine the geometry. So for the pinch grasp, that would be a double point grasp. A pinch grasp is a double PP, a PP grasp. But then if we cannot combine a lot of them, actually we have a lot of combinations. So only with that, we can see that we can abstract from the human hand. So we can actually analyze human grasp by defining what is the geometry that they are conforming to the cloth, but also we can define generic, for generic grippers, what are the grasps that use. For instance, we are able to describe what are the grasp types that all these robots are using. So for instance, in this last one, that maybe is the most complex one, where on one side is using a point against the table, and then a line, they have like a brush that to flatten the cloth. So from this definition of a state that we talked before, we already have defined what is this notation that I had before here, that they had this PP plus the pi E, which is the planar contact of the table. What we did is we analyzed the literature and about robotic demonstrations with clothes, and we saw quite already a variety of the grass types that have been used, but when we check the numbers, you realize that it's basically all these red ones. It's basically mostly focused on the pinch grass, or the PP grass. In addition, this definition allows us to also classify types of manipulations, depending if they are sliding or if they are with the fixed grass, but then you move the cloth. As I said before, the cloth is not fully inside the hand, so you can move the hands and manipulate the cloth, which is basically what we do when we fold, for instance, but also adding and removing strips in contacts, etc. So first of all, it's really important, this grass type, because if everybody is using the pinch grass, maybe it's because it doesn't really matter. So what the first thing we did is try to see how grass type can influence on the manipulation of cloth. And what we did is we used 3 different grippers with different geometries. This first one is a double line, then this other is between a line and a plane, and this last one is the double point. And what we did is we manipulated with a pre-grass cloth. It was the human, the subject that was using the grippers. And we performed, for instance, the task of folding a t-shirt in the air. And we also were wearing this X-Sense suit that was able to collect the motion data of the hands. And you can already see that, for instance, doing this task with only a pinch is quite complicated. So what we can do now is compare the trajectories, which depending on how is the alignment and the rotation point, you see larger or smaller trajectories. But what is more interesting is the acceleration and the velocities. When we compare the velocities, we can clearly see that when using only the pinch, you need to really do a very fast motion to give enough impulse to the cloth so that you can actually fold it in the air. So that basically means that, yes, it's true that the type of grass can influence the dynamics of the task. And if you choose the correct geometry, basically you can get a much simplified task dynamics. And this is, of course, this is a highly dynamic task, the folding in the air, but we got similar results, as I will show soon, with other tasks that are much simpler. So if we look at these 3 tasks, we selected these 3 tasks: pick and place, folded clothes, folding a t-shirt in the air, and trace cloth. We observed humans performing this task. This has done in the literature, has been done with only pinch grasps, but we can clearly see that we as humans, when we manipulate, we use a lot more of support under the cloth so that it doesn't get unfolded. And this is highly also dependent on the type of cloth. Also, for folding a t-shirt in the air, this has also been done in the literature, mostly with a pinch grasp. This work that is also from Adrià Colomé and Carme Torres from our institute also started with a pinch grasp, but they quickly realized that this was a reinforcement learning work where the robot was learning to perform this motion of folding in the air. And they quickly also realized that they were putting more geometry on the gripper, the task could be learned better and faster. So giving, for instance, linear geometries in this aspect could help also the dynamic of the task. And finally, the last one is tracing the cloth edge, which is, of course, is done with a pinch grasp, but is a pinch that has different requirements, because the one that is holding the cloth needs to have a very high friction, while the one that is light needs to have very low friction in order to be able to actually slide along the cloth. So based on these observations, we designed a gripper able to perform a variety of grass. For instance, these pinch ones, but also like providing a support with a plane. That's why it can open the bottom fingers. And also it can provide like a planar surface against the table to perform the double plane one. And so we are still working on developing a novel version of this gripper. And one of the things that we did in the same idea that we saw before is comparing grass type and the influence on manipulation. So we did a subject study where the subject was instructed to do the task as well as they could. We humans can do anything with anything. So we give just like chopsticks, and we can do also folding of clothes. But the idea is that it's more difficult. So with the fingers open, we could do this unpiling and piling of folded clothes, and we did the same with the fingers closed. And especially in the moment of placing, we could observe again, that's similar than before, that the acceleration that you need to provide in order to actually place the cloth well, is much higher when you don't have this support under. So far what we did is, what I explained so far is about grasping. So we can now describe the manipulations that appeared in the literature as succession of grasp types. So for instance, this is the usual one where we regrasp the cloth and then we use vision to localize these grasping corners. In this other one, they use actually the extrinsic contact with the table. So they grasp the cloth and then they add the table contact and they slide it on top of it so that they can identify novel grasping points. And then they grasp it again, they remove the tablecloth and they iterate on that. And this other type is the sliding on the edge where you have a pinch grasp and then you just slide to find the pin. This is clearly not enough. So what we are working now is to adding also location of this grasping. So what we did, we defined a set of coordinates on the table that are subject dependent because these labels of left corner and left corner depends on the perspective of the human, of course. And for instance, this one is represented in this corner here, meaning that the grasp is basically, the cloth is grasping one corner. And then we also have a very basic definition, a semantic definition of the state of the cloth. If it's folded, if it's flat, crumpled, or partially folded, that means that the folded is not finished, or semi-flat, that it needs flattening. And we also have a semantic label to identify the transition between the origin state and the destination state. And here we see an example of how we do this labeling, which right now is actually still manual. We have done this labeling manual, and we are working now on trying to do that in an autonomous way or partially autonomous way. And so what we do here is every change of interaction between grasping or cloth state, we annotate it as a single option, but then we observe that for several humans. And this here we see 4 of our subjects performing exactly the same task, and they do it completely different number of steps, different number of it's like 4 completely different ways to achieve exactly the same task, which is folding in 3 folds, which is what it was instructed to the subject. This we did it with different tasks. This is putting the tablecloth, and again, these are 4 subjects, and it's a completely 4 different types of performing the same task. So with the grasp, with this coherent grasp, we are able to capture all these different variability and of strategies that we can get to accomplish this task. So we are working on this graph for several applications. And one of the applications that we are considering in the context of the work program, which this is a Chistera EU project that we have, this benchmark for understanding grasping. One of the things that we can clearly see in this graph is the segmentation of a task. We can identify this is the beginning, we are grasping the first point, this is the grasping of the second point, then we put it flat, then this is the first fold, this lower one is the second fold, and then we can identify the third fold, which is basically the final fold. This is interesting because this is relevant in the moment of evaluating manipulations. And for instance, in our initial work that we did on benchmarking with KTH in collaboration, we could already find 3 tasks for cloth manipulations where we could clearly distinguish this grasping of the first point, then grasping of the second point, and then performing the actual task. And this is actually not easy ways of doing it. For the grasping the first point or grasping the second point, it might require additional manipulations that are not expected. So this is the first idea, but then we kept working on that. For instance, grasping for cloth, this is true also always, like for rigid objects, but it really linked to function. So for instance, in this case, we see that it's not the same if we have to grasp the same cloth, but if it's for unfolding, or if you need to pick up the cloth to place it somewhere else. And even if you need to place it, is this grasp good for placing? Because depending on what is the cloth, maybe it wrinkles too much that you are completely unable to then place it again flat on any surface. So we think that grasping cloth is actually easy if you don't care about the function, because you can just put any gripper there and the cloth is very soft and you're going to grasp it. But then maybe you cannot do anything with it. Also, the graph allows us to this definition of the task in steps, and now we are working on studying how errors in evaluation and success rates can spread through the graph. So maybe just the first edge of a manipulation, you can do it with some error, but maybe then this error is not relevant for the rest of the task. If it's not relevant or if it can get corrected, then it's relevant to know if it has any value to actually evaluate this independently. So that's a very neat example of that is the task of edge tracing, which normally the normal process of that would be like you have the cloth grasp in 2 points, then you slide over the edge. When you reach the corner, you put the cloth flat and then you place it flat on the table. When you actually learn the grasp from humans, there is more variations to that. There is a lot more of variations to that, and one of the things that we see, this is actually a symmetrical graph on the left and on the right, so you can also only look at one of the sets, for instance. So here, what we see that when we trace an edge, one of the evaluations that you would quickly think of is like how well you can reach the corner. So how close can you get to that corner? But then when we observe humans doing it, we realize that not always the corner was reached and the task was still able to be performed correctly. So what we did is to actually evaluate one of these single edge of placing flat on the table, but assuming different errors from the previous edge of the graph. And then what we did is like, this is the video of the task of placing flat on the table when the cloth is correctly grasped. And then we define a continuous measure of success. We think that it's important also to have these continuous measures, because only success or failure, it might not be enough to actually see enough insights. And we can compute like a percentage of error, and we also did some performance of error depending on the area of the cloth. Then the idea, like here, some results is that depending, of course, this depends a lot on the type of cloth. So for instance, we tried with 3 different types of clothes. This would be the big tower, which is the one you saw in the video. And well, it seems that yes, it's true. You don't need to reach. You can get up to 12% far away from the corner, and 12% being of the total edge length. And once you start getting farther, you can get to 25% here, and you're still fine. But then after that, you start seeing a lot of errors. So it's true. This is important when we evaluate edge tracing to take in consideration that maybe it's not really that relevant to be able to reach exactly the corner. As opposite, when we try to evaluate a full task, here is the task of putting a tablecloth. In the benchmark paper, we propose the option for the authors to actually report only the partial task, so the first grasping, the second grasping, the placing of the table. But then if you actually want to evaluate the whole task, you need to provide a measure of task quality of the whole task. And of course, this is highly dependent on task. This will always be like that. So what we propose here is to check how well the tablecloth was located against the table. Like if it was rotated or if it was more longer in one side and on the other. That's basically what you do when you put a tablecloth. And of course, that means that if a system of robots can place a tablecloth very, very badly, so hanging a lot from one side, but then the system is able to relocate the cloth and put it correctly, it has to have the same success ratio, the same success measure than another that does it maybe in a single manipulation. So that's what we've been working so far. But of course, this is an ongoing project, which means that we are actually using this grasp and working in parallel in a lot of different projects. For instance, in recognizing of these scene states, as I said, once you define the grasp and the contact with the environment, the configuration of the cloth is simplifying, because there are not that many ways, especially when you are doing a specific task. So now we are working on a deep learning system to train to recognize these different grasping states and interaction with environment states. We are also working on cloth state estimation, because in addition of this very basic recognition of flat or crumpled cloth state, we need to also have some parameters able to so that we can go to grasp, for instance, to localize cloth corners. And also we are using some topological measures on the edge of the cloth. We are also using this graph as a framework to provide explainability to a system. In a robotic manipulation, we have several artificial intelligence processes that work in parallel. And then we are going to use this graph as a common framework to provide a coherent explanation. This is the Coherent project that just started. It's like a month ago. And so this project really, I cannot really show anything yet. We are also working in this benchmarking of cloth manipulations, including also benchmarking and measuring of these grippers that we have. Now we put them on the robots and we're going to measure the same that we measured, but with the robot. Because of course, when you have the human in the loop, maybe the human is actually solving a lot of the things that we see. And we are also working on development of skills like edge tracing based on force feedback. As we've seen, like the force feedback, we think is very important, not only rely on vision, but also to be able to feel the cloth and understand what is going on also from force feedback. So that's our group. In parentheses, we have the women. We need more women in robotics in general. And this is our lab and our robots. We are working with Jaguar robots. And that's all. We're doing perception of rigid and non-rigid objects, planning for perception and manipulation, and also learning from demonstration and reinforcement learning, in addition of what I've been talking today. So that's all. I don't hear anyone. Okay. Like, maybe I was alone all this time.
No, thank you for the really great talk. I actually have a questions about these coherent graphs. Like, are they object specific, like one graph for the napkin, and then if you would do one for the shirt, is it a new graph, or can it be integrated into one bigger one?
It could be integrated, but of course there is particularities of every object that make it different. So basically what would happen is that you would have an even sparser graph, that you would have more options for grasping from the first graph to the first grasp to the second one. You will have a lot more possibilities how to do it, that maybe they are depending on the object. And you see, it depends on how you simplify. At the end, you need to decide what you want to simplify. And so we actually work on bridging, like having all the tasks that we have in a single grasp. So then we don't care about what's the object. But then it's more difficult to understand maybe other things.
Thanks.
And I also have a question about the graph. And actually, I was wondering if this kind of graph is completely comprehensive, or if you consider that you may also fall in a state that is not in the graph. So when you're interacting with deformable objects, it's kind of tough to already know all the possible states of the graph.
No, definitely, that's true. The good thing about learning from humans is that there is already a lot more happening than what the robot can do. But definitely one of the things that we have as an open question for the future is the ability to learn new states when we are able to actually execute, because we are still not at the edge of executing with this graph, so that with this graph on the robot, because we are still learning to recognize these states. And once we can do that, then if we don't find any match with the states that we already know, we can actually think about learning new ones online.
Okay, thanks.
Hi, Julia. I have a quick question. So your taxonomy, have you considered how the human hand fits into the taxonomy, where you might have like 5 pp, right?
No, actually, well, it's one of the things I still want to do with a data glove, like try to see how we can transfer. But my idea is to actually simplify in the same way that the virtual fingers nomenclature. This actually was done with this overall idea of these papers from the 80s that define the virtual fingers and the opposition forces. And if the fingers are making force in the same direction, they are considered one single virtual finger. So my idea is that if you are doing this would be a planar or a line. They would not be considered 5 points. And if you are doing a pinch, this is also going to be considered like a pinch, like a 2 points, not 3 points, unless you are actually doing. But again, because you don't have shape of the object, that will never happen. Like when you have a round object, it can happen that you are actually doing 3 forces in 3 different directions. But when there is no shape, like it's like the object collapses to nothing. And then like, but it's still like, it's one of the things that I still want to do, like to map these geometries to the human hand. You can do it like yourself, like thinking about, but yes, I still haven't really collected data. And I'm not sure it's just with the data glove, it's gonna be, no, without actually considering contact. Because then you need to estimate the contacts, like with it from the data glove.
I agree. Thank you.
Michael?
All right, I think we don't have any more questions for Julia, so we will move